but 4 people to show up. My name is Lori Lalonde, and I'm the user group of this CTT-DNUG is the short form for it. I've been running this user group for, I don't know, 6, 7 years now. I don't know how long it's been. It's been a while. Anybody here new tonight? Yes. What's your name?
Emma.
Emma. Where are you from?
I'm a co-op at
TD.
Yeah, I go to Waterloo. We're both in the same class.
Oh, so you're both at University of Waterloo. Excellent.
Yes.
What year are you in?
We just finished first year, so it's the co-op before second year.
Oh, excellent. And your name?
Reno.
Reno. Welcome.
Thank you.
I'm Bridget.
Bridget, welcome. And Bridget's from Conestoga. She's in the suffering program there, so welcome. And hopefully graduating this year, they get back from the strike.
Hi, I'm Jason.
Jason, yes, I've seen your registration, and you're a supporter as well, so thank you.
Yeah.
And you've been here before.
Yeah, I've been here before, yeah.
Okay.
Scott.
And then welcome back, Steve. It's been a few years.
A few years, yeah.
So I just want to say, yep, come on in. So I just want to give a round of applause to our sponsors. Northdale Software is a full season sponsor for our user group. So without them and without Microsoft, who's also a season sponsor, we wouldn't be able to pay for the room and bring snacks and things like that and host events like this throughout the year. So thanks to our sponsors. And for our organizing committee, it's myself. There's Dan Wilson, who's right there, who doesn't have a Twitter account apparently. But the rest of us you can find on Twitter. There's Ken Sanarelli and Arlen Noguera. They're generally at the .NET session, so you may see them in a couple weeks if you go to that. If you have any questions, feel free to reach out to us through the Meetup site or even on Twitter. But for Dan, just Meetup because he has no Twitter. And if you love to tweet, not like Dan, just use those hashtags for tonight, machine learning, Azure Notebooks, and then our CTT-DNUG hashtag as well. And after the meetup, go on to the page and rate us because we like to know, was the session something that you liked? Would you like to see more of it? Let the speaker know how he did. And just because we are planning on bringing this back as a second run in January. So because you're here tonight, don't sign up for that one because it's going to be exactly the same as it is tonight. It's going to be an opportunity to let people attend that didn't get to attend this round tonight. And upcoming events, Microsoft's hosting like a Mission to Mars session. So I don't know if anyone here has gone to the last one. They held it in Toronto. It's like, I think like a half day or all day hack fest where they actually have different exercises to walk you through to building bots and using AI and natural language processing, Azure Search, all this good stuff, and it's free. The Toronto event's November 21st. And then for our group, in 2 weeks, we have Dave Lloyd coming from Toronto, and he's going to talk about SQL Server data tools. That session will be held at the library that's on Blockline Road, attached to St. Mary's High School, not here. So generally, our .NET sessions are held there on the 4th Wednesday of the month, and then we run our Xamarin and other sessions here the 2nd Wednesday of the month. And then Hacker Nest is hosting their next meetup Monday, November 13th. Oh, it's Monday. Yeah, at Myovision. And it looks like Myovision, it's at their new location because it's on Glasgow. So I didn't know that they moved.
Catalyst 147. They're in there.
So it's a
it's a whole new venue, yeah.
Okay, so that's worth going to. Okay. Hacker Nest is a lot of fun because it's a great way to meet people. It's all like a social event essentially. And usually there's like 100+ people that go every time. It's a really great opportunity to meet new people in the community. And so without further ado, I'm going to hand it over to Dexter, who's going to start us off on a machine learning workshop. Thanks, Dexter.
Thank you. Intro is, my name is Dexter Fitchuk. I do machine learning at TD's Innovation Lab in Communitech. So what we really get to do that's cool is play with all the new tech that comes out and try to see ways that a bank can leverage it, where in a corporate environment, it's a lot harder for them to adopt new frameworks and then validate them and even just have time to play with them. So I basically get to go look at like trending GitHub repositories, see what Facebook and Google have been open sourcing lately and play with all of that. And then the other cool thing that I get to do is I get to basically ramp up our co-ops on machine learning. So we have students from all different disciplines that don't have any experience. And then our devs, our designers, and our BAs, we all do a machine learning bootcamp for, but we do it as a full day thing normally, where the first half of the day is just like teaching them the basics and then giving them the tools that they'll need, and then we normally do a challenge in the afternoon, so they'll like compete with the full-time staff, the other designers, developers, and it's a lot of fun having that competitive side to it instead of just doing a normal workshop. So it's really cool because I think for applied machine learning, a lot of people normally think that you have to have a strong math background or you need to know what's happening on the behind the algorithms, but realistically there's amazing tools out there where it can abstract a lot of it and you learn by doing, and you learn a little bit more about different algorithms to use for different scenarios, how to optimize them. But it's really cool because just like any other library or framework you'd use, you can really learn to leverage this in your own development without having a huge idea what's happening on the back end. So yeah, I'll just dive right in. So I just say this at the beginning because this can take a while to download. So if you do want to do this locally on your own system, you download what I would recommend is called the Anaconda stack. So it's a ton of data science libraries basically for Python. If you don't have a computer, that's okay because I will post the slides and all the stuff for this if you do want to follow at home afterwards. But if you don't want to download this, which I would recommend to everybody instead because it can take a long time to install, it's a lot of libraries, they go right now to Microsoft Azure Notebook service. And then basically you can just sign in with any Microsoft account that you have and you should be okay. And then you can actually run all this stuff in the cloud without having to worry about installing all the Python libraries, all the data science tools, and all of that. So it works really, really well for this because afterwards we'll actually just clone the starter repository that I have on GitHub right into here and you'll be good to go. You don't have to install anything on your computer. So as I'm going through these first slides, I'd recommend try to get signed in so we'll all be at the next part, and then it gives you a few minutes if you have any problems. So, let's see. So, just to dive right in, how many of you have heard of machine learning? I'm assuming most of you because you're here. But how I really view machine learning is it's a practical subset of artificial intelligence. So it's a little bit more applied than more practical, I think, than artificial intelligence because it's usually for specific problems. You know what your input would be and you know what your output would be. And it involves basically taking a set of training data and building a model that can either classify new input or predict the output of different data. So it's just kind of like you're predicting the future from different data. So I find that to be really cool because you can train a computer on millions of records that a person could spend their whole life reading and never understand the nuances, the patterns, what the trends are in it. But you can actually train a computer to identify these in a way that we never could. So there's two types of machine learning that we'll kind of talk about. These are the classical types that are still like very dominant today. So the first one is classification. So you can think of classification as being like binary. Something is 1 or 0. You can think of it if you're predicting photos, it's a cat or a dog. You know what your output classes are and what you're trying to figure out. Regression, on the other hand, is a bit different. Regression is when you're trying to predict a value, but it won't necessarily be a specific class. So a great example is if you were trying to predict the price of a house. Your inputs could be how many square feet it has, number of bedrooms, number of bathrooms, and then your output would be an actual monetary value. So it could be like $12,050, or it could be just $100. It could be basically any number between that range. So it's more for when you're predicting something like stocks or housing or trying to get an actual score of something, where classification is just we know the different things we want to predict. It could be boy or girl, hot dog or no hot dog. There's lots of different ones. So the flow of a machine learning project is a lot different than if you were doing a normal like software engineering project, if you were building an app, if you're building a website. It's completely a kind of new, or it's not a new way of approaching things, but it's a lot more of a research project, it feels like, and a lot more trial and error, but also just having fun and testing different theories, because you kind of come up with a hypothesis that you could predict something, and then you'll go through all this analysis to see if that hypothesis is true, and you can validate it. So the first step of it is basically the data mining step. So this is when you find all of your data that's out that you want to use for your training. So it could be from you just find a data set online. There's tons that are hosted for free. It could be that you're building your own. Maybe you're harvesting people's tweets and you're going to eventually label them as being positive or negative and do a sentiment analysis. There's many different ways depending on your problem of where you would get your data from. And in time, like, each of these could end up being really fast or really slow steps in the process. It depends how lucky you get for your actual problem. So the next step after that, so you've got all of your data and you need to start you need to do feature engineering, it's called. So it's when you're trying to get a little bit more of your data, you're trying to clean it up, you're trying to remove maybe if you have blank fields or anything like that. So it's just the cleaning of the data. So then there's other things you might have to do, like plotting, and this is a lot more of the analysis, where you might want to notice trends, and then you might see one different column is more important than others. You might want to then focus a little bit more on cleaning that and trying to get more out of it, or generating new different columns out of it that you can deconstruct and get more out of. And the final step, by sure, it's the funnest step of it, is the training and evaluating. So it's when you feed all of your data that you've now cleaned into different machine learning algorithms, and then right off the bat you can start getting a baseline score of how accurate it is, if there is actually a trend. If you're getting 10 or 20% accuracy, you know something is wrong. You have to go right back to the previous step. Usually if there is a clear correlation between something, there is a pattern, you'll be able to see after just trying a few different algorithms with their default parameters. Just by looking at the score that you get. And then after that, there's tons of optimization you can do to keep driving that score up. But it's really easy to tell right away if you've done something completely wrong or your hypothesis has failed. There is no real correlation or trend, because there for sure is some things that in the world are truly random and we can't predict. And this is when you basically learn that. So for the data mining step, a few ways to find different data is literally just Google what it is and either you could type in like lung cancer data set if you wanted to do a little research on that. There's other sites, like there's tons of open data government sites. There's this site called the UCI machine learning repository that's all this open data that's free for anyone to use. And then there's another website called Kaggle, which basically is an online data science competition platform, but it also has a different area where anyone can post data sets and then anyone else can download them and collaborate on them, work on them. And it's really cool. I'll show everyone after this, but you can actually see what people have done to different data sets and use that as building blocks for your own. Because sometimes it can be hard, especially starting from scratch, to know how to just dive into a problem when you get a data set. So it's cool being able to see what other data scientists across the world will do, how they'll visualize data, the types of algorithms they'll use. I'll show you guys afterwards, because I have a lot of fun going on there, and I've definitely learned a lot from really, really smart people. So then that pre-processing step that I brought up. So it could be removing irrelevant features. So features are basically just a column. So if you think of a spreadsheet and you have different columns for different attributes, some of those might be irrelevant. Like if we're trying to predict what someone's favorite food is, we could maybe like say you had the number of toes that they had. That's probably a feature that's not too relevant to the type of food that they like. You could drop that. And you'll want to do this because otherwise your algorithm will try to find linear relationships between these things. And maybe there's just this, someone coincidentally only has one toe, or so. This is a really weird example. I haven't used it before. But say someone has one toe, that could automatically skew your data set because that's an outlier. It doesn't actually impose a relationship or impact the end thing. It just is coincidental. So you want to really do a little investigation to what you actually think would be relevant and what wouldn't be. A better example would be a primary key. That's just an auto-generated value and has no real relevance. So say it's when you signed up, like I'm maybe customer number 300, that might not have a lot of relevance. Or you could decide maybe it is. Maybe if you're looking at a small set and you want to see, maybe you did like a coupon offer and it was everyone after like customer 300 was eligible for the coupon. Maybe it is an important factor then because you can see over time when they were involved. So you really have to think critically about it and do a lot more of an investigation, and sometimes just think of how different columns could impact your thing. So a lot of people skip this step and they don't think it's as important. They'll just take a CSV and cram it into a machine learning algorithm, and sometimes you do get great results. But for the most part, the feature engineering is really where you can get the most out of your data, and you'll get more promising results than the ending when you're just optimizing a machine learning algorithm is really when you'll get maybe like a few % gain. But for this can impact it. It could increase it 10% or whatever, however good you are at doing it. So the other thing is for different types of data, you might have to scale your inputs. You might have to you do have to transform text fields to numerical representations. With machine learning algorithms, everything you feed into it basically needs to be a number. It will perform different mathematical functions on it and steps, so you can't just feed a word into it. That being said, for things like natural language processing and things like that, there's ways to tokenize and basically give each word in a sentence a numerical representation. So you get a series of numbers, and then you can feed those, and these algorithms can actually find numerical patterns or linear patterns between that fed in array of numbers as opposed to the text string. So we're not going to go into natural language processing stuff, but it actually is pretty easy. There's libraries out there. So in 3 lines of code, you can take a text field and automatically turn it into a numerical representation and then use the exact same algorithms. But kind of breaking apart some of the syntax that people use for data science, because I definitely, when I was learning it on my own, I didn't have a mentor helping, and just I didn't learn what X and Y meant when people talk about data science, and this really threw me off because you'll see in a lot of people's reference code, your X, if someone refers to it, is basically your input data. So that's all of your Excel spreadsheet of all the input that you would then use to predict an output. So then your target column is also called your Y, or your output label, your class. There's many different names for it, but in code, I mostly see it just called the Y or labels. So this is what you want to predict. So you can see for this data set, it might be, I think they're applying for a loan. So you can see a few different features in here. So we have like loan amount, we have the term, interest rate, grade, home ownership, annual income. And then you can see we want to predict if they're basically fully paid, charged off, different things like that. So it would be a binary prediction because there's only 2 different things it could be, either fully paid or charged off. So it's really easy though when you start to think of, you open a spreadsheet and you see a column and you say, hey, what if I could actually take all the data that I do have on this, train a machine learning algorithm, then in the future, if I have someone's loan amount, term, all this up to the annual income, I could actually predict with a certain degree of accuracy if it will be fully paid off or charged, or fully paid or charged off. So this is really where machine learning is cool, and this is called supervised machine learning because we have our input and we have our output. We are basically telling it, so when it's learning, it will feed in all of these different values, and then it will see if it guesses its prediction right, and if not, it will go back and basically punish itself and keep optimizing itself until it actually corrects itself when it does these predictions. And it will do this thousands and millions of times until it is with a certain degree very accurate. So another cool way to visualize this is one sample of data, which is basically our one input column or a row, is we turn into a 2D matrix just like this, and then one feature would just be a row like this. So you can see it's not that hard to visualize it, especially if we go back. So this would be a feature. The loan amount is one of our columns. So again, just a feature. And then one sample is one row of our input. So if you just look across, that is one example where this person applied for $5,000. So then something else that you might have to do in your pre-processing is it's called categorical variables. So there's a few different things you can do. One is called one-hot encoding. People also, it's called, like the function for it is called get dummies. It's really strange. But say you had a column that was categorical and the options were red, green, or blue. So it was one of those 3 people had. So it might be like nail colors, red, green, or blue. So instead of feeding that in or just saying, I'm going to make red 0, green 1, and blue 2, that would actually impose a linear relationship. So it would try to find some numerical representation of a pattern between those 3 colors. But when you do this categorical variable encoding, you can actually make what's almost like a truth table where you'll make 3 new different columns. So you'll have one for red, one for green, and one for blue. And then you'll have it's true for red, and you know it is already going to be zeros for the green and blue, but you can do this automatically, and then this will remove that linear relationship it's trying to impose between if you had just one column that you then mapped it to certain categories. So I know this seems pretty complicated, but you guys will see when we go over some code. You can do this in one line of code, and it really is just knowing when you have a category or something that you need to transform it into something like this. So I hope I'm not overwhelming anyone, and I think when we look through some code together, it will make a lot more sense, a lot of it. So another thing could be scaling inputs. So specifically neural networks and some other machine learning algorithms like it better if the data is between a range of 0 to 1 than 0 to infinity or a million, something like that. So again, in one function, you could just take your input and would automatically scale it down to be between 0 and 1. So you can see this is just a really easy example. If you think of a movie review, someone might give a movie a 1, a 3, a 5, or a 2. You could actually just scale that to be, like 1 would be 0.2, 3 would be 0.6. You would just divide it by the max. So it would be, you just divide each of these by 5, basically. So the final step of it is the training of a model. So this is when the first step you do always is called splitting your data. So a lot of people don't realize when they go into this that you can't just train a machine learning algorithm on all of your data, and then if you want to see how accurate it is, feed back that data and get how it performs on it, because it's basically remembered a lot of that data that you've trained it on, which isn't fair because you won't get a generalized view. It's like if I was quizzing you on something but I told you the answer before I quizzed you, it's the same idea. So what you do is you take, say, 80% of your data, you set that aside for training it. You take the other 20% of that and keep it just for testing afterwards. So it's never trained on the testing set. You only afterwards will then perform an accuracy test on it, so you can see on data that it has never seen or been trained on if it generalizes well. So if it's actually able to make accurate predictions. So it's really easy to do this in Python, which is what we're going to be doing this stuff in. So there's a function just called train test split, and all that I'm doing is right here where it says iris.data, that's actually like your X, it's the same idea, and iris.target would be your label, your Y, so they're just passing that in. They've decided to use 40% of their data for the test size, and then you always want to set the random state to a number, and then you can just leave it as that. And the reason for that is because otherwise it will do it randomly shuffles the data, which is good because we want to have random samples. But if you set the random state, it seeds it. So even though it's a random shuffle, it's reproducible every time. So you won't just keep getting different shuffles of data, because if you kept getting different shuffles and you kept training the same machine learning classifier, it might perform better sometimes depending on the type of data that it got. Maybe it has more outliers in the training set than the test set. So it's not necessarily fair to then have that, and you can't really see if when you're optimizing it, if it's your optimizations or if it's just you're getting lucky with your different split of data. So you always want to set the random state. I know this is confusing for people that might not know what seeding a random number generator is, but it basically will just mean that you can reproduce your results every time, so you know that you're actually making improvements to it. Yeah?
I have a question. During the training, it is a human who evaluates the result. I mean, you input some data, the model gives you some results. It is a human that says, is this correct or not?
So you can actually, the benefit of doing this split is we then get a basically test set. So then we can feed it in afterwards our test set and get all the predictions that it thinks it is. But because we know what the output should be, we can then compare those predictions to our Y test. And you can get an accuracy score without you actually having to sit through and review it all, because we know what the output should be for the test set, and then we can have it perform predictions on the test set. So you don't actually have to sit there and manually review them afterwards. You can have it all automated, so at the end you just get like an accuracy score of how accurate it is on data that it hasn't seen. So I'll show in the code too after, and it will make a lot of sense, I think. So this is a quick visual as well to see training and test set split in your data. And this example is actually really good because you can see the problem without randomly shuffling. You can see that we have 5.6 and 6.7 as our output here, and nothing in our training set is actually within that range. So you can see that it's almost, we're not going to get these outliers or these values, so won't learn what necessarily happens to predict these high values. So it's a nice little visual that I realized afterwards is faulty, but also teaches a great lesson on it. So this normally you don't have to worry about when you actually have millions of records, like having classes that are uneven, because it will do a random shuffle. But sometimes you might want to afterwards, when you're doing your, like you get your accuracy score, you can actually see which class or which numbers it's predicting more right. So if you were predicting how accurate something is at doing cats and dogs, you might have a score of 75%. But then if you look, maybe it's 100% accurate at predicting cats, but it's only 50% accurate at predicting dogs. So sure, the average score of that would be 75, but you can actually see where you then need to focus your efforts, that it's guessing stuff is cats a lot more than dogs. And I've had another one where I had 1 million records and only 200 of them were a separate class, and then everything else was other. And the machine was really smart. It realized it can just guess everything is other and get 97% accuracy, even though it's actually not predicting anything of value. It just knows that that was how it could optimize itself the most. In the easiest way, it took a shortcut. So And the next step, basically, when you're going to teach the machine is picking a learning algorithm. So SciKit-Learn is going to be the library that we use for Python, and it has tons of built-in, like any traditional machine learning algorithm that's out there, it has built in, and you can change them basically just by declaring a different one. And then it's the same syntax for actually training it. So it makes it really easy to, you could basically write a for loop of all the different ones you want to try, and you could have it iterate and actually evaluate all of them and compare it. Just because the syntax is the exact same, other than you just specifying the algorithm. So again, we'll see in the code how simple it actually is to switch between these two. And it's a really great basically starting point to build a machine learning model from, it's not completely from scratch because we're not coding in the algorithms, but I really like the idea of doing it from scratch instead of just finding an online like drag and drop thing or using some platform or something like that. I think it's a lot cooler to actually break it apart and do a lot of this engineering on your own. And the tools are out there, and it can be really confusing. I've seen when you Google how to start with machine learning. So this is what I found to be the most, this is how I learned the most, and now I can step into any new tool or framework and learn it a lot faster than if I think I had gone the other way. So how do you pick an algorithm is another great point. So Scikit-Learn has this little kind of like mind map style thing. It can also be kind of weird because it only includes a few algorithms and there's literally hundreds of them to use, but there's also some great things to figure out what kind of problem you have. So if you look at the start, say you have less than 58 samples, this is a really valid point. That's not enough data to do machine learning. You need to get more data. I would actually up this to be a few hundred at the bare minimum, but if you have 1,000 or thousands of records, that's a lot more promising. And then if you're predicting a category or if you're predicting a quantity, you can see it kind of maps into regression or classification like we said before. We won't talk about clustering or dimensionality reduction, but it's a cool little way to start and see what kind of problem you have basically. So we won't go too much into parameter tuning, but once you've found a few machine learning algorithms that you really think are promising, you're getting high results with just the defaults, I consider those being like candidate algorithms. So now these are ones you want to maybe fine tune and put a little more time into actually playing with the parameters and tweaking to see if you can then, the gains that you can get performance wise on your data. So there's different things you can do like grid search, a random search, or hyperopt, where it will basically, a grid search is you give it a ton of different parameters for each one, like values for it, and it will do every single combination of those. So if you had 10 values for maybe like depth would be one, 10 values for number of leaves for like a decision tree, and then 10 values for, I can't think of another parameter off the top of my head, just another parameter, it would actually train that algorithm with 1,000 different combinations and then find the optimal parameters that score the highest. So it will do like the first of each of those categories and keep doing every single one until it's gone through them. So it can take a while to actually do the hyperparameter tuning because you have to just leave your computer sitting there sometimes, and it could take hours, it could take days to train depending on how much data you have or things like that. But that's why you really want to come up with a few great candidate algorithms before just doing the same one every time and then just investing that much time in it. So I've listed a few of my favorite algorithms here. We're not going to use many of them other than random forest today, but I thought I'd include a few extra things on these slides because you guys will have access to them afterwards. So if you want to go back and reference or you want to know next steps, I thought it would be meaningful to include it here. And then the last thing that I think it's the last thing, talk about before we go into the code is underfitting and overfitting. So actually this slide is better. So overfitting is when your machine learning algorithm is so fine-tuned to your specific training data set that it doesn't generalize well. So this is a great example where you can see there's many outliers that it's learned basically to predict, but it's not a very generalized idea because maybe an outlier might not be as impactful. And then I really love this underfitting example. This is when your model is too generalized and it's not good at doing predictions at all. So you can see where the points are plotted and you can see it's just a straight line. So it's really not promising at predicting anything. And then you can see the just right area is when you are getting this nice generalized center line basically between your data. So you can actually encode plot all this out and see how your algorithm does predictions along this line, which is a really great way to basically see after you've trained some initial models, if you're training it too much on the same data, or if you're not training it enough, maybe you need to do more iterations on the same data so it gets a better idea of it, until you basically find this sweet spot here. just ignore where it says this increasing bandwidth parameter. That's just from where I stole this from. But it's, I think, a really valid point because a lot of people think that like neural networks, you train or you tell them how many times you want them to go through your data. So it could be 1, it could be 50, it could be 100. And a lot of people think, oh, I'll just have it go 1,000 times. I'll leave my computer for maybe a week. I won't use it at all, and I'll come back and I'll have a really promising machine learning algorithm. But the truth is, it will get really great at just predicting the data in your training set and nothing else. So if it gets fed data that it's never seen, it's between new ranges that it hasn't seen, it won't give you a great generalized prediction. It won't be accurate like if it was more generalized for new examples. So I'm not going to go really too much into these metrics, but this is almost like when I was talking about how many times is it predicting cats right and how many times is it predicting dogs right. There's other metrics like recall and precision, and then there's also like recall is the number of positive, like true positives it actually predicts properly. I think I always get confused reading this out. Yeah, what % of your predictions were correct? So the accuracy is really basic. But then what % of the positive cases did you catch? So the recall is actually the number of positive classes that you predicted correctly. And then, yeah, I'm not going to dive too much into this because I still get twisted, but I thought I'd again put it there so you understand some different metrics. So now we're about to dive into the code finally. We're going to be using something called Jupyter Notebooks. So it's a really cool, it's almost like an IDE where you can break up and do a lot more investigation, but with your code. But say you have you break your code into cells, and say your code, maybe to load a data set in, it could be a few gigabytes. It can take 20, 30 minutes, depending on how large your data set is, just to load it in. So you don't want to then, every time you do a tweak, have to rerun your whole file and have to wait. So what you can do with these cells is actually have the first cell load in the data, then every code cell you run below it will already have run that. So you don't have to run your whole code sequentially from start to finish again. You can actually pick where you want to start in the middle of it. So we'll, basically we're going to, your steps would be data mining, pre-processing, splitting the data, training, and then evaluating to basically go through a full machine learning project. So we aren't going to have Python issues because you're all going to use that Azure notebook platform. So then afterwards, if any of you do want to set this up on your own system, you can download that Anaconda stack, and here's some instructions of the commands you can run to actually get it up to date with all the libraries that you need.
What's that slide you had before? Issue with 2.7?
So a lot of the libraries don't have compatibility with 2.7 now, and a year ago this would have been different. A year ago everyone was only using 2.7 for machine learning, like all the libraries were only compatible with that. But now from what I found, if you have any real problems going on, it's probably because you're on 2.7 and you need to go to 3.6 or 3.5. But that being said, there is some older libraries where I have to go back to 2.7 just to run them and do some analysis because they haven't added compatibility for 3.6. But it's cool when you use the Anaconda stack because you can actually create separate environments on your system where like this would be a Python 3.5 environment called ML, but you can create one that would be like ML 2.7 and you can switch between without having to reinstall everything, which is really nice. So. And I put some practice things here that people can do like on their own if they want afterwards. This is just a fun visual. It doesn't mean anything, so don't try to read into it. But yeah, now we can actually dive into code. So for those of you that didn't bring a computer, you'll be fine just following along. We're going to walk through it. For those of you that did, I welcome you to basically follow along with the code because it can be really fun tweaking and playing with it and having it run in your browser. So first we're going to fire up the Azure Notebook site. So did everyone get in okay that tried? Cool. So I just learned about this the other day when I was talking to Lori, and let me see. I wasn't signed in yet. So I want you all to go to your libraries. I zoomed in quite a bit here. And then when you get in here, hit new library, and we're gonna do from GitHub. And then I just want you to put it's Dexter Fitchuk / ML Bootcamp.
What's the URL for the what?
For the notebook thing?
Yeah.
I just Googled Azure Notebooks.
It's notebooks.azure.com. Yeah.
Okay. Thank you.
There you go. I'm so used to just searching everything. So once you've then done the new library, put in this GitHub repository, just Dexter Fitchuk / ML Bootcamp. then you can name it anything you want for the library name and library ID. It doesn't really matter. So I'll give everyone a second before I go off of this. If you have any problems, please let me know though. I haven't had any problems yet with this, which is really nice.
Are there any issue using Anaconda on Windows?
No, it's actually really nice because it will have its own command line that it will basically install too. So you run everything from it.
So then how you switch on Windows from 3.5 to 2.7?
It's the same, so you get like your own terminal almost on Windows, just like this. And just like you would on OS X, you get the same commands where then you can create different environments and run them from the Anaconda prompt. It's called on Windows.
What's the file that controls the environment?
I'm not sure the file. It's a built-in thing in the Anaconda stack though. It's just, they have a conda command where I can actually, while people are doing this, where if I want to create a new environment, I would just do conda create -n. So I'm going to do ml test, I'm going to call it. And I'll do python equals 2.7. And then give it a second, it finds the packages that it needs. Takes a few seconds. So you can see it actually shows you what it will install for that environment, and then you would just hit yes, and it's the same on Windows and OS X. And then for those of you that do want to use this on your computers afterwards and download Anaconda, we're going to have something that automatically opens the notebook up, but all you have to do once you've installed the Anaconda is go in your terminal and type in Jupyter Notebook. And it's really cool because it actually just opens in your browser and you have this now full-fledged Python IDE. So this is my file structure of my computer. But now if I go to like the bootcamp and you click the notebook file, this is exactly what we'll have on Azure, but this is how you run it on your own computer. So now,
What if you are in a situation when you are required, some tools required 2.7, other tools required 3.5?
so you have to kind of separate them and stuff, the parts that you can do, and it's annoying to switch back and forth between the two environments, but you'll usually like do what you need to do in 2.7, save it to a CSV, go in your 3.6 environment, load that CSV in and back and forth. So I haven't had many times where I do have that problem. It's usually if I've been trying to just do like a separate like visualization or something just for fun is usually when I've had to switch back to 2.7.
I was trying to build a Google IE experiment project, and some tools require 2.7, other tools 3.5 on Windows. Yeah, so it's quite messy.
It's really annoying. It's for sure like when they like by not having backwards compatibility with Python 3, it's really annoying in a lot of cases. So did everyone get to this? And then you can hit import. Whoops, you can make this longer. So if you hit import, it should import. Everyone good? That's following along? Looks like it. Awesome. So it's really cool because it will actually take it just for my GitHub repository here. So it makes it really easy for workshops like this. So then when you get to this screen here, there's actually a lot of junk that is in this folder that I left there purposely. So then after this, there's other examples that you can go and kind of look at. We're only going to focus on one. So if you go into this Titanic folder, we're going to be doing what's called the Titanic data set. So this is a really morbid hello world of machine learning where we're basically going to have the passenger list from the Titanic and predict if someone would survive or not. So it's really sad, but it's weird. This is like the guide that I see the most, just like a hello world style one for machine learning projects. So a very morbid theme to start off the night. So we don't always get a nice little definition dictionary like this, but can everyone see this okay? Am I blocking you guys back there? Okay, awesome. Oh, it's a little much. So we basically are getting a stata dictionary where these are all of our different columns that we have, and it's telling us what each of them is. So we can see survival. So survival is a binary field. So it's 0 if they didn't survive. It's 1 if they did. And this is what's going to be our Y, or our target. We want to predict this column. So now we're looking at the passenger class. You can see there's different things. The sex is just their gender. Their age is the age in years. We have all these different columns, and then embarked is the port of where they embarked. So there's these 3 cities that they could have embarked from. So you can see for this data set, they actually have notes on it, which is nice too, so you can kind of see. So the passenger class is actually part of a socioeconomic status. So it could actually be impactful depending on which class they were, if they survived or not. We won't make the full assumptions, but we can make the assumption that it could have something to do with it. So let's see. So we'll just dive right into it. So you can see what's really cool is this description here. If I double click, it's actually all written in Markdown. So in here you can write stuff in Markdown. Then if you run it, it just formats it nice. So in between all of your code, you can actually have really nice descriptions. It's not like you're just doing a slash and a comment after things to describe it. You can give really nice descriptions. So then we're going to start with importing a few different libraries. So our first one's going to be called matplotlib. It's just for doing some nice plots really easily in Python. And then if I do this command to do it in line, it will actually embed it in the like below the cell instead of saving it as an image like it normally would. And I'm importing something called numpy, which is just for doing different computations and filtering stuff out. And then I'm importing something called pandas, which we're going to use basically to load in our data. And then it will basically, you can think of it just being like a spreadsheet in here, but we're setting it all to one variable. So all you have to do to run each cell is you can either click it and then hit cells and then run cells. And you can see when it has this star, it means it's actually running. And when it turns to a number, it's done running that actual cell. This one takes a few seconds the first time because it will be the first time on this environment you're using it. But see, now it has 1, it's completed. And you can look at the order of these numbers is basically the order that you ran them. So it's useful for if you see that you've actually got 21 at this or something, and then this hasn't been run as recently. So now if we go here, this is a really simple command. So I have this CSV that's in that folder we cloned that's just called train.csv. So we're just going to run this cell and it's going to set this all to a variable called df. It basically is just a short form for data frame. So every time I load in a data set and I don't have a really good name for it, I don't like calling it data. It's typically just called, people put df because that's actually the type of object it is too, as a data frame. So then the other cool thing in Jupyter is I can actually just put the object, any object here without doing print or anything weird. And when you run it, it will actually just almost do like a dump of it. But it knows for data frames are actually like a CSV style thing or a spreadsheet style thing. So it actually will plot it out really nicely for me. So I can inline with my code instead of having to, like the old way would be just running the Python script, saving the CSV, opening it in Excel, which is great most of the time. But if you have something that's over like 100 megabytes, it will take a really long time to do that. So being able to, as you're going through your code inline, seeing how your data looks is really powerful. And that's what makes Jupyter so great, is that we can actually run the code cell by cell and go back and forth without having to run it all. So right here is great because we actually get to look at, besides just that list of the dictionary, what the data looks like. So we can see the name, we can see their gender, the age, all of those things before. We can also see things that are called, so NaN fields are basically if it's a null value, it just puts NaN here. So that we need to find a way to handle any field that has a null value because we can't feed that into the algorithm. So one of those steps might be, should we replace them with zeros? Would that make sense in this column? If there was more numerical data here, we could replace all those null values with the mean and maybe think that that would be a safe bet. Or the other thing that we're actually going to do is we're going to just drop all of the entire rows that has a null value, because I think that we can get away with without having those columns. So you can see we actually have 891 different rows. So we have the records for 891 different passengers. So I think it will be safe to lose a little bit, but we'll make sure. So you can see right here, I'm taking my data frame and I'm going to do this df.drop command, and I can just like this list a few columns that I think that I could drop safely. So if we go back so I can talk through it, these are all things I'm just assuming won't have relevance. So you can see this ticket column, the naming scheme is just really weird for all of them, and almost like this, they didn't have forms or databases when the Titanic was going out. So I think it's pretty safe to say that people were just making up ticket numbers when you look at A/5.2151. Then some people just have integers. I'm going to make an assumption that I can probably remove ticket, that it won't have any relevance. Same with the name column. I'm going to assume that when they were going to lifeboats, they didn't say like, oh, are you Mr. Owen Harris? Oh, you're not? Sorry, I'm not going to allow you on the passenger boat. So I'm going to drop the name column. And then the third one I think I'm going to drop is this cabin column, because just from scanning it without doing any other analysis, I can see there's so many null values in it. I can probably get rid of this column and I won't miss anything. And that seems like it will make more sense than removing all the rows with a null value. So just like this. And then you'll see I put this weird axis 1. It just means so it drops it row or column wise instead of row wise. So I'm just going to do that, and you can see we'll actually drop these 3 different columns. And then the last thing I'm going to do is this drop NA command, which means it will drop all of the null values afterwards. So once I drop this, if there's any columns afterwards or any rows that have a null value, I'll then drop them, which I don't think there's too many, but you can see this is an example right here where I don't have their age, so I'm just deciding I'm going to drop it, because this wouldn't make sense to set a 0. It would really skew my data set if it thought it was a newborn or something. So
Do you have IntelliSense? For example, there for axis, should I suppose that axis 2 means you drop the rows?
if you make it, I think axis 0, it drops the rows.
Okay.
I don't really use axis 0 because I don't fully understand what it would do all the time. Most of the time you'll see you just drop the rows. It's more if you had, I think, different, like instead of just primary keys here, you had some other kind of column or something, so you'd want to drop those instead.
Going back to my IntelliSense question, so if you type df.drop, it will give you suggests what's the syntax there? Or?
Yeah. So in the way you do it in here, I actually have been using this for a year and I didn't know how to do it. If you just hit tab when you are like after a period or something, it will then give you the suggestions of what you can do.
And if you choose drop, then it will go further and says these are the parameters you can use.
So I don't think it actually gives you the parameters, which kind of is
So
one of the downsides
help?
of using this. So I usually will Google just like pandas drop, and then they have really good documentation for all this. It definitely is not the like ideal way, whereas if you had this in a full IDE, but I think it's worth it for being able to break up and do your code in these cells. So you can see I can just run this, but I'm actually going to put just the df here again so I can view it after it runs. So just like that, it dropped these 3 columns and it dropped all of the rows afterwards that had a null value. So you can see this is our new data frame. So again, just like we'd expect, it dropped those columns and it dropped all of the rows with a null value. So we've already started cleaning this pretty nicely. And instead of having to go through all this, it skips some records. You can actually just click the side and it will make it in its own little window basically, so you don't have to have it completely in the way. So now, the next thing that I'm going to handle is, I scrolled too far now, is we want to basically now look at this and what do we have to do to transform the data. So we see a lot of text. Sorry, I thought I had dropped a name already. We see a lot of text here, like sex. So this is something where it's categorical. It's either 1 or a 0. So we can easily make it that. So I'm going to go down here. I'm going to create a new column called male, and it's going to be either binary, 1 or 0, depending on if they're male or female. So then using this other command where it's just np.where, I can see from my data frame, I'll make it so if the sex is equal to male, then it becomes 1, otherwise it becomes a 0. And now after that, I can actually go and I can drop the sex column, and then I'm also going to drop the name column here because we already discussed that that's probably irrelevant. I don't need the sex one anymore because I have a new one that's called male. That is if they're male or not. So now if I run that, see, it's not very exciting because I already had the output from before, but you can see we now have this male column, and like we would think it's 1s or 0s, and we've dropped the sex, and now we've also dropped the name. So our data is looking pretty good. We've almost handled a ton of pre-processing, turning all of the different text columns into some sort of numerical representation. Then the last one here is this embarked column. So this is where we actually have 3 different categories. We have S, we have C, and we have Q every once in a while. So this isn't as easy to make a 1 or a 0 because we have 3 different ones. And this is also a case where you wouldn't want to say 1, 2, or 3 because that's going to impose a linear relationship between the 3 of them. So this is where we do that get dummies command. So if we take our data frame, we concatenate our original data frame with now we're going to do this PD dot. You don't have to know these functions off the top of your head. I have to Google these all the time. But this get dummies function, and then we're going to do it on the embarked column. It's going to make that truth table that we saw before in the slides, where it's basically the 3 different columns and then a 1 or a 0 for if it's true or false. So then I'm dropping the embarked, and now let's look at the data frame again. And you can see it took our C, Q, and S and made it now to be each their own column instead of being one column where those are the options. And now if it's an S, it has a 1 there, and the other 2 of them are zeros. And vice versa for the C, the S, if we go to Q, will be the same. So we've created these 3 new columns and dropped the original embark, but now we have this nice data set where everything is numerical. We finally can now feed it into some sort of algorithm. Yeah?
Why make them zeros and ones when you can make them true or false?
Make them 2 or 4s? Or
True or false.
true or false? Because there was 3 options for this one, so that's the only reason we couldn't do true or false.
In a single column, there's only going to be 0 or a 1, right?
Oh, like right here?
Yeah.
Oh, you mean instead of doing 2 of them? Or
No. In a single column,
yeah.
its value is going to be either a 0 or a 1.
Yeah.
So why don't we use a boolean?
A boolean, because for if we go up to the embark, there's 3 different options that it could be.
He's saying why it's 0 and 1 instead of true and false. You know what I mean? Like
True and false. Because we have to feed everything as a number instead of a letter. So if your data was, you'll find a lot of data sets where it might actually have true or false, and you still have to transform that into being zeros or ones. Sorry about that. But does that make sense?
Yeah.
Just because it will now try to do different calculations on all of these, so that's why you need to have it as numbers instead. So
if there were 10 different, you have a matrix of 10.
it can grow your data set a lot, and there is eventually there's tricks that if you're doing like really advanced stuff, they'll do like a sparse matrix where the zeros it will leave as blank columns, and then on running through each record, it will automatically fill those with zeros. So because if you had like a data set with 100 different columns, you can imagine, or 100 different categories it could be, you can imagine then doing this table, having 100 different columns where you're storing all of that grows your data set quite a bit, and it can fill in your memory really easily. So that's why they eventually, for some things, they'll do these sparse matrices where all the zeros will be blank, and then when the algorithm feeds it in, if it sees a blank field, it will automatically put as a 0 on runtime, so it doesn't fill your memory. But for the most part, for most data sets, you're usually pretty good to do this, unless you're working with something that's like a few gigs in size. But a lot of data sets, they're pretty clean, just being a CSV by nature. So even if it's a few hundred megabytes, you can get away with this.
So Victor, can we take like a quick 10-minute break?
Yeah, no, this is the perfect time to do it actually. So yeah.
All right, so we'll take a 10-minute break. You guys can have a bio break and have just some more snacks and refreshments, and then we'll pick it up again at 7:30.